My name is Paul Offord. I work for a company called Advanced 7, but I also lead a project called TribeLab, and I'll explain a bit about that later. So here's what we're going to cover today. We're going to quickly, we're encouraged to do this to tell you about us. So I've got one short slide on that. We're going to look at a Wireshark plugin called Transum. It initially started out as an external project, but now is part of the standard Wireshark build from 2.4 onwards. And we're going to look at the relevance of that to something called the RTE model, Response Time Element Model. We're going to look at ways of analysing network delays, particularly for the bulk transfer of data. Challenge these days is that a lot of the traffic that we're looking at is encrypted. So if we can see a slow response from a web service or a web server, how do we know what's going on? How can we go to the owner of that service or the software house and tell them it goes slow when it does this? We can't see what's in the packets. So what we're going to do is look at how we can match up the packets with web logs, starting with IIS, Microsoft IIS, but then also looking at Apache logs. And then I'm going to do a small piece on other logs and traces. So me, I'm getting too old to do this. I've been in the industry quite a while, as you can see. I think probably the most interesting thing is I've worked on the supplier side of the industry and I've worked on the end user side of the industry. So I've seen the challenges from both sides. I'm leading this project called TribeLab. TribeLab is all about sharing information with people who are interested in troubleshooting problems in systematic ways. And you'll see that in the bottom of the slide it talks about community.tribelab.com. That's where we live. About 1,300 of us participate in the community. You can join the community quite easily. You can even access most of the data without even joining the community. So you might want to look at that. I've been doing problem solving for a long time. I still enjoy it. It's still find it quite exciting. And I'm a keen weight trainer. You can see from my physique, can't you, that I'm a keen weight trainer. Okay, so Transum and RTE. So if we consider communication in a network, what we're looking at is process-to-process communication, from a browser to a web server, from a PC to a file server, from a web server to a database server. It's all process-to-process communication. And in many of the systems that we look at, probably more than 90% of the systems we look at, they communicate in the same pattern. And that is, they send a request and expect a response. So here I'm not looking at packets necessarily yet. We'll look at how this maps into packets, but we're looking at these things called application protocol data units. We send a request, we get a response. The time it takes for the server to process the request, we'll call that service time. And the time experienced by the browser in sending the request and getting the full response, we'll call that APDU response time. So obviously there's a difference. You can see if you consider increasing time down the slide, there's a difference in the elapsed time from service time and APDU response time. What do you think the difference is? What makes up that difference? Network, absolutely. Network time. So all the things that you've learned in all of the other sessions here at SharkFest about retransmissions, dupacks, TCP windowing, all of those things, that's what's going to cause that delay there. And we'll look a bit further at that. So if we consider all of the different protocols that are available in our environment, as I said, many of them work in this request response manner. And even things like SCSI commands over your storage area network, they work in a request response manner, as do even Windows API calls. You make the call, you get a return, you get the data back. So many of these things can be looked at in that way. And if you're used to looking at things like application performance monitoring systems like App Internals or App Dynamics or any of these ones, you'll know that you can see a breakdown of these request responses in those systems. So, of course, if I make a request to a web server, it may require one or more requests to a back-end server. So here I'm just showing a simple example. We've got one request going to the web server, results in two complete two requests to the database. Nothing too complicated, fairly straightforward. So let's dig into this a bit further. Consider the situation that the user clicks on a button, the browser spends some time processing that, maybe runs some JavaScript or whatever it does, and then it sends a request to the web server. The request is too big to fit in a single packet, and so it gets split across a number of packets. And here I'm just looking at packets that contain payload, data, TCP segment payload. And the easy way to filter for those is to just use the filter term TCP len is greater than 0. So that just gives us the data packets. The time it takes to send these packets, we'll call that the request spread. So the thing that impacts request spread is, as I said before, latency, TCP retransmissions, window sizes, all of those sorts of things. They're all going to impact request spread. Then we get some service time, and then we get the same thing in the other direction, and this time we're going to call it response spread. Same idea, just the time it takes to transfer the data from the web server back to the browser. The total time from the first request to the last response, we'll call that the APDU response time. So we have these four distinct messages, measurements, APDU response time, service time, request spread, and response spread. APDU response time being made up of a sum of the other three. So you can see that just using this simple model, if I can view these figures, I can very quickly determine first, do I have a problem? If I have a high APDU response time, then there's some sort of issue, whatever it might be. Then if I've got a high service time, I know the problem is in the web server. And if I have a high spread time, I know the problem is in the network. So I'm showing this for a web server. I hope you understand that this is equally true for a PC to its file server, for a web server to a database, even for an application server going out across the internet to some external service. This all holds true for all of those types of systems and applications. We get some client time, and then the page is rendered. So just a straightforward, what happened? This connects to this type of pattern. And of course, the user's experience is from the mouse click through to the page render. So in that case, if the APDU response time was small, but the user's experience of the response time was large, where would the problem be? In the client side, yeah, in the browser, absolutely. So simple transaction, mostly if you click on a button in a browser, it does a lot more than just one request and one response. But whatever the complications are around that, this whole model still holds true. So I'm going to illustrate this by looking at a problem. I'll start off with a problem which is using SMB2, Microsoft's file server protocol. And basically it's Acrobat Reader reading a PDF off of a remote file server and loading it up into Acrobat Reader. And it's taking an awful long time. Very, very slow. So let's have a look at that one. I should explain here, I'm using this thing called Workbench. Don't be too fazed by it, it's just a way that I use to organise my data. Everything that I show you during this session you can do without Workbench. Workbench is freely available from the TribeLab website if you want to use it. There are some things I will do that are just shortcuts, and I'll explain what I'm doing at that point and how Workbench is helping me. So just a way of organising data. So just quickly, over here on the left, what I have is I have an Object Explorer. In this Object Explorer, I have a mixture of things like files, but I also have web page links and all sorts of other things just in the Object Explorer. Across the top, we have Toolbox. I'm sure many of the tools you recognise there, including Wireshark, of course. And then over on the right-hand side, we have this thing called Transformers. I'll explain what that does for us later when we use it. Okay, so I just want to grab... These are just my notes. So let's open up the file. And what I'm going to do is I'm going to switch into a profile that I have set up for Transum. So what Transum's doing here is it's adding this additional information into the frame. And you can see all of those values that we spoke of, APDU, response time, service time, etc. And now all I've done is I've right-clicked and then done apply as column and then added them up here into my packet list. The beauty of doing this is that I can simply do that, and then scroll to the top, and I can see the slowest response times. It's that easy. So you can see here that there are some that are quite worrying. This one here, for example, is a read for, I don't know, 52K or 55K of data, and it's taken 3.5 seconds. Not so good. Apparently, the service time is very high, but also we have a very high response spread. Now, if you remember where I captured this from the original diagram, if I just show you that, I captured this here. So I'm looking at it from the perspective of this PC. And the trouble with this is that the service time value I see can be inflated if the data that's going in that direction from the file server back to the PC, if that is delayed, it can lead me to think that I've got high service time figures. So, of course, the trick here is do dual tracing. Trace there, and compare the two. But actually, in this case, there's a big hint, a big giveaway, which is the response spread value is quite high. And what that's telling me is I've got congestion or something's going wrong in the direction of the data coming back from the file server back to my PC. So then once I get into that, let's take this one here. What I can do is I can use this field here. If I right-click and copy the filter term as a value, and I paste it up here, and then I reorder back into packet order. Here's the read again. It's on the actual request. You can actually move it to the response if you want, but it's on the request. Here we have another response. Now, the thing about this is, this request here, if you look in the SMB header, you'll notice that it has a message ID, 724. This response here is for message number 721. And so what you can, because of SMB2 tries to accommodate high latency, high bandwidth links, it enables you to overlap requests and responses using this thing called credits, this credit charge thing. So in fact, that response there is not the response to this one, this request. And I can keep going down here. And I've got more responses, so that response there, again, it's not the right one, and I can keep going down until I find the correct response, which should be the last one, which is that one there, 724. Okay, now the other big giveaway in here, of course, is these black lines in here. So you can see dupacks, TCP retransmissions. I think I've got some fast retransmissions. So I'm sure you'll learn from sessions with Betty and Kerry Rogers and Jasper and all those people. They'll help you figure out what's going wrong at this point. But what you do know is we do have a network problem. Okay? I just need to make sure I tidy this up each time, otherwise I get in a right mess. Yeah. Okay, that's a very good question. Sometimes it does, and sometimes it doesn't. One of the issues is that if you take SMB, lots of protocols use a single connection, and you'll just see one session on one TCP connection. SMB isn't like that. SMB multiplexes multiple sessions across a single TCP connection, so you have to drill down a bit further. And in fact, it's a bit of a challenge in transum. You have to do a lot more checking of what matches what and what session you're on and all those things. But that is a good question. That's why. It's a bit more complicated with SMB. Any other questions? Okay. So the next example we're going to look at is HTTP and SQL. So browser talking to a web server talking to a database to get dynamic content, variable content. Quite a simple system. Again, the users are complaining that it occasionally hangs for 30 seconds or so. We have traces taken in a number of places, on the PC, on the web server, on the database server. So let's have a quick look at that one. Grab my notes again, just in case. And okay, so this is the first time I'm going to show you Workbench doing something that you can't actually do with Wireshark. So this trace here has been captured using Windows NetShell trace command, which produces a format called .etl. Wireshark can't read .etl files unless it's running under Workbench. So what's happening here is Workbench is going to transform the file into a PCAPNG using these transformers over here on the right. Hit the button, and there you go. Okay, same deal. Order, and order again, and straight away we can see there's a problem. APDU response time of almost 30 seconds. Now, the user did complain that it was when they clicked on an instructor link, so we know we're in the right area. So what I'm going to do now is I'll reorder by packet number, hoping that I keep on the right packet, which I do. And now I'm going to just pick out that session in the same way as I did before. Copy the value, paste it into there, hit return. So we see the request, and then we see the response come back in two chunks, 1460 bytes followed by 1256 bytes. I've got TCP len is greater than 0 here. If I take that out, excuse me, I can see things like the acknowledgement for the request. So you can see the acknowledgement happens really quickly, and then we've got a 30-second delay until we actually get a response. So that's all good. So let's now, just want to check my notes. Yep. Okay, so now I'm going to take the trace that was captured on the web server. Open it with Wireshark. This one's a bit bigger. Now, what I need to do is I need to find the matching entry. So the way I'm going to do that is I'm going to take the TCP sequence number, and I'm going to copy that as a filter. So it's just copied it as a filter expression. I go back into my other trace, I do Control F to find, I paste in the filter term, and I hit the find button. The first thing it's taking me to is the ACK. This is just because the sequence number is in an ACK that's earlier. If I keep hitting find, eventually I'm going to... Oh, okay. There we have the correct packet. Okay, so perspective from the server, sure, still a high service time. So we know that we're on the right length here. But perhaps the biggest giveaway here is that just after the request is received, there's a database call. And the database call, the response time for the database call is almost the same as the overall response time. So if we look at the bytes in there, you can see it's got the word instructor in the bytes, which looks as though it means we're in the right area. And in this case, what I'd do is I'd take the select statement, I'd go and see the DBA, and I'd show him that and say, every time the users get a slow response, this is what's being executed on the database, and it's taking 29.4 seconds to respond. Okay? I've gone quite fast, and we've covered quite a lot. Any questions on that lot?
Why you don't merge them? Wireshark, you open them with the different Wireshark. Why you don't merge the captures together?
You can merge the captures together? Yeah, you can. I didn't need to for this because if you look at the topology of the system, you can see that a browser request will come through this adapter here, and the request to the database will go through the same adapter. So as long as I look at that trace there, I'm seeing both sessions.
I think I lost the first minutes of your presentation.
Okay.
So I think that when you export the packet, you have something more than you have normally Wireshark.
No, that's normal Wireshark. Using the Transum plugin, which is part, is part of Wireshark 2.4.
Okay.
It's a standard part of Wireshark 2.4. In fact, it's not enabled by default. You have to go in and enable it as a protocol. So you go to Analyze, Enable Protocols, and tick the box against the Transum entry, and that will switch it on. Yeah? Okay, that's all right. I didn't say that earlier, so you've helped. Okay then. Just tidy up again and go back to my slides. So one of the things is that the idea of capturing on a server is something that was fashionable, then went out of fashion, and actually is becoming fashionable again. And the reason is because people are running services in things like AWS, which is what you're looking at here. We want to capture network traffic, but there is no way that we are going to get a tap or a span in the AWS network infrastructure. And so we have to start to reconsider capturing on the host again if we want to see that traffic. And this was a slide, it was actually sent to me the day before I came here. That's why it's a little bit fuzzy, because I copied it out of an email. But my colleague is designing a solution for a customer who needs, we're supporting them as they transition quite a large insurance system into AWS, and we wanted visibility. And so we start to look at the idea of capturing on the host again. Now, when you capture on a host, it does nothing to the CPU, I can tell you. You'll not even be able to measure dump cap or even a net shell trace running on a server. It's just insignificant. It takes a very small amount of memory, very small footprint. The thing, of course, it does is it generates a heck of a lot of disk I/O. But then if I'm in AWS, I've got this massive elastic file store, and I buy that by the minute, terabyte by the minute, or however I'm paying for it. And so I've got the possibility of actually capturing quite large amounts of data for quite a low cost. And that's what we're looking at here. So I think we're going to be doing more of this. If you want to see what's happening on the other end of the network, you might be responsible for the internal network inside your organization. Then, of course, we we either go across an AWS direct link or into the internet. We're going to traverse that, and then we're going to get into the data center. And if you want to see the other end, you're going to have to do things like this. Does anybody else have any insight or experience in doing this type of thing? Just out of interest? Okay. So just in summary, APDU response time shows you the client's perspective. If you've got a big number, there's a problem. If you've got a big service time problem, then there's a problem with the service. And if you've got big spread values, then there's a problem with the network. Very broadly, that's it. So the idea with this is, of course, we're bombarded with millions of packets, but the ability to take a top-level view like this and order the packets by APDU response time and then drill straight in, that's quite attractive. I think you'll agree. Sure. It is available in T-Shark. Yes, it is. Yeah. They're all available. Yeah. I know minus Z statistics. I have no idea what it would do with that. I don't know. It doesn't work, as far as I know, it doesn't work with the statistics package. Okay? Actually, there's one thing I should show you. Let's go back just very quickly. One thing you can do is if I choose statistics from here, IO graph, you can see that I've added in APDU response time into my IO graph definition. I've made it a line graph, sum the Y field just here, and then that's the field I'm using, transum.art, APDU response time. And then you get a nice graph like this. Let's switch off the packet one. And so we can see spikes in the APDU response time. In fact, it's more spectacular with the other trace. Just grab that one. That looks a bit more interesting. So you can see what you see in red is the APDU response time, but you also see it quite closely correlating with the TCP errors. And also, if I switch on all packets, you can see that it's quite closely correlating with the actual load on the link, or the load being measured by the Wireshark. Okay. I must move on, otherwise I'm going to run out of time. I can see that happening. So, if we don't have a high APDU response time, then the problem isn't with the service that you're looking at, and so what you need to do is move on to another service. If the PC is talking to another service at the time when the user has a problem, then let's go and have a look at that instead. If we've got a high service time, get the matching traces to confirm it really is a service time issue, grab the information out of that and go and see the service owner and explain what's happening. And if we have high spread times, then we need to focus on the network and find out what's going on the network. Okay, so network delays. This is a slightly different example. What we have here is you can see a bunch of VDI desktops on the left-hand side of the slide. They're accessing a web application through this, it's a Palo Alto firewall actually, and a load balancer. The characteristic of this particular application is it shifts a lot of data from the web application back to the user, large amounts of data. And if you do an RTE analysis, what you find is you get high response spread values. But the question is, how can I go a bit further and find out what's going on? So we have traces captured on the ESX host, and we have a trace captured just in front of the F5 firewall. So basically, we're looking each side of the, next to the F5 load balancer. So basically, we're looking each side of the firewall. That's what we're doing here. So let's have a look at that one. Okay, so I'm going to start by looking here. Just have a quick look at this trace. But I'm going to change my profile, and I'm going to look at this profile here. So I'm interested in this particular value here, round trip time to ACK. Now what this is it's a measurement of the time that has elapsed since the data packet that we're acknowledging was received and to the point where we send back the acknowledgement. And in this case, it's the difference between that SYN and the SYN ACK, obviously, in this particular example. So the round trip time to ACK is telling us how long it is since we saw the data packet and we are now seeing a response to that data packet. And I can right-click and apply that as a column, and that's how I came up with the RTT to ACK value. Okay, so looking through here, it all looks okay. Don't see any particular higher volumes. See some stuff going on here, which we'll have a look at later. So I have these two traces, and they're taken at two different points on the network. So I'm going to use another Workbench feature called Matcher. All Matcher does is it just matches packets based on certain criteria. In this case, mainly it's using the 5-tuple and the sequence number. So you can do this manually. Okay, I'm just doing this for speed. So let's just match these up quickly. So I've matched the packets. Through earlier analysis, and you'll just have to take my word for this, we've noticed a problem starting at around packet 82, so I'm going to look at that. Just make sure I haven't, So I just want to change this. Okay. So Workbench is just firing up 2 copies of Wireshark at the correct matching points in the trace. I don't know why it does this. That's, okay. So what you see here is that here we have the round trip time to ACK as experienced at the F5 interface. And here we have it on the other side of the firewall. So what we're saying is the data came out of the firewall and went to the VDI session and got immediately ACKed within, 105 microseconds. But from the perspective of the other side of the firewall, that operation took 118 seconds. So what you can see here is that, just to explain, this is keeping these two in sync, so I can track back through the traces. So if I go back to the top of this one, you can see here there isn't a problem. The numbers are all low. And we come down through here, starting to get slightly bigger here, around 12 milliseconds, but this one's 9 milliseconds. 15 milliseconds, 40, it's going up, 40, 118, yep. So you can see that we've got low values up here and high values down here, so something is happening across that firewall. So armed with that information, we're able to go back and see the firewall engineers and look at the state of the firewall in a bit more detail. So this is what we saw, just to give you an idea. Data enters the firewall, comes out of the other side, gets acknowledged really quickly by the VDI desktop. The acknowledgement comes back within less than a millisecond, and yet we see a total round-trip time of 118 on the other side of the firewall. Here's the firewall CPU load. It looks as though it's just very bursty, unless you look at this note added down here by my colleague, where he points out when the utilization is 0, it represents no data. And the basic situation is that during this period of time, it's so busy it can't actually respond to the CPU polling to get the statistics. And so actually this was an overload of the firewall. And that was due to a certain set of complications around the rules that were being used. The rules were rationalized, the load was reduced, it fixed the problem. Okay? So the takeaway from this, for me, is... The takeaway from this is this use of round-trip time to ACK to look at the performance of the traffic in one direction is really useful. There are other things you can do, and if you attended Kerry Rogers' session yesterday, and if you didn't, try and get a copy of it, there's loads of stuff you can do around using things like the TCP trace graph in Wireshark to look at TCP performance. And that's a great way to do it too. But this is just something that you can do to actually look and really pinpoint the cause of the problem. Questions? Whose idea was it to start a session at 8:30 in the morning? On the last day of all things? I don't know. Okay. So we talked earlier about the challenges if you have encrypted traffic. What on earth are we going to do to see inside of those packets? How can we help the owner of whatever web service or web server? How can we help them determine what's causing the problem? So there is this log that's recorded on an IIS, a Microsoft IIS server. It's called the W3SVC Log because that's the standard log format that it's using. It's space-separated variables. The timestamp is nearly always in UTC. In fact, in all the ones I've ever looked at, I've never seen it not UTC. You can actually override it. There is a way of changing the setting, but nobody ever does, which is probably just as well if you're working in multiple time zones, because it could get very confusing. The timestamp for each entry, bizarrely, is the time that the acknowledgement is received to the HTTP response that went out to the client. And that's because that's the time the log entry is actually written into the log. So it's the timestamp of the log entry. There is a value called time taken. Effectively, it's the service time. So we can actually view service time in these logs. And we can open it in Excel, which I'm going to show you, and it has a header row that shows you, it explains what each column means. So let's have a quick look at that. Now this actual log has been captured on an Exchange server, an Exchange email server that's running active sync support, and the IIS portion is what's running active sync. This was just something I was able to get hold of, so I've used this one. If we look at it with something like Ultra Edit, you'll see that it's just a text-based log like that. You'll see things in there you recognize. So, we've got date, time. This actually is the IP address of the server itself, the version 6 version, and here's the version 4 version. Then we've got the method that was called and the URL, and then we move on to things like this thing here, which is the query string. So lots of lovely information. So that's the log. Let's have a look at the actual network trace. So this network trace matches the log that we've just been looking at. Now I'm interested in one particular user, and I'm hoping that the IP address is still in here. Yes, it is. So I've got the address of the IP address of a user that I'm interested in. So let's filter on that. And then we start to look down here. APDU response time of 540 seconds. Okay? And again. And again. What on earth is going on? Let's just grab my notes. So what I can do is actually filter for this data in Excel, from the log in Excel. So there's a workbench way of doing this, which is actually just to drag and drop Excel onto here, but that won't work if you try that in Windows. So I'm just going to show you the Windows, the standard Windows way of doing it. So if we fire up Excel and we open a blank, you've got to do it this way round. Open a blank spreadsheet, then open the log, and then choose delimited. It's not tab delimited, it's not comma delimited, it's space delimited, and press finish. And now I have the information in here, all nicely in the correct columns, etc. So let's get rid of the first 3 columns, because I don't care about those, first 3 rows rather. I'm going to embolden that. I'm going to do a freeze, view, freeze on that. That's just so that I can scroll up and down without my headers moving, like that. And now I'm going to actually find the same IP address that I'm interested in. So, select the whole sheet by clicking in the corner, click on Data, click on Filter, and it's the client IP address here. Unselect all of them, come down here, and just select the one for the user. And the user was, in fact, Joe, so I'm good. So you can see what's going on here, and, oops, sorry. So we can see the active sync requests being made here. And what I'm going to do now is I'm going to try and look further at these strange entries. So I'll go back to this here, and the timestamp I'm interested in is around 22:33. Now this network trace was captured in September. September in the UK, we have daylight saving time called British summertime, and it's 1 hour ahead of GMT. So actually in the logs, I'm interested in 21:33:01. So 21:33:01. Whoops. (21:33:01). Same thing, 540, 540, 540. Oh, a quicker one. So let's come in here. 540, 540. 15 seconds. 15 seconds. Sorry, this is in milliseconds. I should have explained. This is in milliseconds. Then about half a second. Back in this one, a bit more than half a second. So given the measurement differences between the two, you can see that we've got a very similar pattern going on in here. So actually what's happening here, we can now go into the query string, and The giveaway is this thing here that says command ping. If you do a search on the internet on active sync protocol and you look at command ping, what it tells you is I'm polling a folder to find out if there's been any change to it. So let's think about what you might be doing here. I've got an Android phone, it's got an Outlook client on it, and I want to receive messages into my inbox when they arrive. I want to receive them on the phone. Back in the day, the way that it used to tell the client is it used to do some sort of push using UDP protocols, but that doesn't play across the internet. So instead, we do this thing called long polling. We issue a request, in this case it's a thing called a ping, and we basically say to the server, time out in 540 seconds if you don't get anything, but if you do get something, then return to me and tell me you've got something. And as soon as we time out, we immediately issue another one of these pings. Send the ping, wait another 540 seconds, it times out, send a ping, wait another 540 seconds. Now in this case, what's happened is, we send a ping. Let me just increase this a bit. So we ping, and then we've got a short one. Now what's happened here, quite possibly, is I've done a ping, and actually something's arrived in my mailbox 15 seconds later. So if we go back and look at this column here, sure enough, up here we still have ping is the command. But then if we go to the next packet, which happens very quickly afterwards and executes very quickly, and we go into here, we can see that this is now sync. And if you look that up in the protocol, it says you are trying to synchronize the folders, the inbox on your handset with the Exchange inbox. Now, I know this is a very specific example, but I hope you can see that this can be, if you synergize this and you can map this into any number of different applications, you can use the same techniques, use the logs in the same way to find out what's going on at a point in time when you can't see inside those packets. One thing you can do with Workbench, just for your interest.
One question.
Yeah, of course. Sure.
How are you able to time the HTTPS encrypted typing with Wireshark?
Yeah, how does Transum do it? Yeah. Okay, it just assumes that if it sees a turn, it's a change from a request to a response. So it sends a request on a TCP connection, and if it sees another request, it adds the number to the request spread, so it adds up the request spread values, and then as soon as it sees the direction change to going back the other direction, it says, that must be service time between the last two. So that's how it does it, and then it does the calculation in the same way on the responses. It keeps seeing responses, it adds to the response spread, then it issues another request. I've seen another request. I need to start a new transaction. Yep. So that's how it does it. Good question, though. Good question. The thing I was going to show you here was just that you can open this log in. This is something else you can do in Workbench. If I change my... So you can see that I've opened up the log here, and I can get access to all the same data. So, for example, for that user whose IP address I've forgotten already, I think it's somewhere here near the beginning, if I remember rightly. Oh, yeah. So I can do the standard sort of Wireshark stuff, right-click, applies filter, selected, and I just get all Joe's entries. You can do that with IIS logs at the moment in Workbench. In the next release, you'll be able to do it with basically any format of log, including Apache, actually. But that's not quite there yet. So, okay. So let's talk about Apache logs. actually. We've got to summarise what we've learned. So, IIS logs, space-separated format, timestamp in UTC, measures the time to the ACK for the response, so it's a bit longer than a service time, but it's good. It's a value called time taken, so that's the value you'll see in the column header. Standard on IIS 7 upwards. On earlier releases, you just have to enable it. It's there, but it's just not enabled. You can open it in Excel in the way that I showed. It's got headers, and Wireshark can open it in Workbench. So, Apache logs, considering that the Apache log and the IIS log both are based on the same log standard, then not surprisingly, many of the features are the same. Space separated. Timestamp now, sometimes I see it in local time, sometimes I see it in UTC, but in most large organisations it will be in UTC, simply because of the multi-time zone issues. The timestamp actually shows the time the request was received, so slightly different to the IIS version. You can include service time with an additional log parameter called %d, and that will give you the service time in microseconds. You can open it in Excel. There isn't a header row, which is a bit annoying. This is what it looks like. Really, not much different to the IIS log. As you can see, pretty much the same sort of stuff in there. You can actually change the content of each of these lines in the log. I'll show you how to do that in a second. So you'd need help. You might need help from your web engineers, your server engineers, to help you set this up, because %d is not enabled by default. They have to make a change to a thing called the httpd conf file. You can see the %d entry in each of these formats. So I've got 3 formats defined. They've all got nicknames: combined, common, and combined IO. And down at the bottom, you can see combined goes to var/logs/access log. So that's where the actual log will be written. So it's all there in the HTTP configuration file. That's how it ties the two together. You can open it in Excel in just the same way that we did the IIS log, exactly the same. It doesn't have a header row, which is a bit annoying, but you can still add yourself in a header. And in the future, Wireshark will be able to open it with Workbench, but not right now. I'm not going to do the exercise again, because actually the exercise is pretty much the same as it was for the IIS one. Any questions on any of that? So other logs. Well, of course, we're being drowned in data coming out of our machines. Splunk has made a whole industry out of this, dragging together machine logs. There's some really great information in application logs, in server logs. We have this thing called ETW tracing. My Windows PC, out of the box, is generating 600 streams of diagnostic data without me doing anything. So, we don't use a fraction of that right now. And we can use things like strace for Linux and sysdig. Strace is incredibly powerful, loads of options, a course all on its own to learn how to use it properly. But you can get some great information from that, particularly if you get the opportunity to work with one of your Unix engineers, and they know how to do this. So I'm going to have a quick look at one example. This is it's a trading system. We have market information on the left-hand side. It's delivered into this gateway box, and then that gets delivered out to an enterprise service bus, which is actually a TIBCO EMS system. Quite common stuff if you come from a trading background. Just to explain the operation, the message comes in from the left in one format, gets queued up on the input queue, gets parsed through a parser, gets put on an output queue, then gets pushed out into the enterprise service bus. Complaint is that it's incredibly slow. There's a massive time lag between the prices appearing in the market server and the prices being published on the topic queue in the enterprise service bus. So much so that they're treated as completely stale. It's completely stale data. So this is an example of the log from that system. And what I've done here is I've picked out one particular message. So each message, each price has a message number, and I've picked out one particular message you can see here. And what we can see is that up here you can see here's the record being received by the gateway box. And so we have a timestamp associated with that, which is 1541. Sorry. Do that again. Which is 1541.16. And then we have the same message going to the parser. So we see it arrive at the parser, and in fact, that is at the same time again, 1541.16, hardly any difference between the two. But then we have to go a long way down the trace until we get to the point where it actually gets published out to the event queue, to the TIBCO event queue. And the time difference between the two, you can see 1541.16 at the top of this trace, of this log, and we're 38 seconds later before it actually appears in the output queue. So, here's the thing. Everybody thought that the problem was with the MPLS cloud because they had network stats that showed that the MPLS cloud was very heavily loaded at particular times of the day. And there were other measurements that they'd made that proved that actually messages were being delayed being delivered into that gateway box. Now, the reason they were being delayed is because the input queue had an absolute maximum length of 10,000 messages. And what happened was it was hitting the top of the message queue and then stalling and stopping, receiving any more stuff, but there was loads of stuff queued up inside the gateway waiting to be published. Now so here's the good news. We've proven that it's not a network issue, except there's a firewall, it turns out, between the gateway box and the TIBCO. The firewall had some really complicated virtual mapping in it. It was totally overloaded. The sender couldn't send the stuff fast enough to keep up with the input rate coming into the inside of the gateway, and that was what caused the problem. They made a change to the firewall, reduced the load, fixed the delays from the sender, everything ran smoothly. So the takeaway from this is we've got those logs, we've got timestamp information in there. If we want to look each side of that firewall at that time, we can get those timestamps, use those, and then drill into the network traces, because the network traces obviously could be colossal. This was a very busy system, and so you need some way of getting a handle on where the problem actually is in the trace. And the final example I'm going to tell you about is the way that a Windows PC or a VDI session, or in fact Citrix XenApp users, the way that a browser discovers a proxy. So in this case, it's using the Windows Proxy Automatic Auto Detection Service, WPAD service. And I'm sure you've looked at network traces and seen WPAD messages in the network traces. Now, the question here was, actually, if you looked at what was going on the outside of in the network traces, there wasn't anything, there was no smoking gun, nothing that showed that there was a really big issue with proxy resolution. But if we use a trace is available to us, and it's called the Win HTTP trace, we can look at these proxy interactions. So if we look here, you can see in this first one, we send a request to resolve, to find out if there's a proxy for this particular URL, and you can see the response comes back in, I don't know, 5 milliseconds. Next one, response comes back in 4 milliseconds. Next one, 5 plus seconds. Next one, we're now into 4-minute territory, just almost 4 minutes for it to actually figure out whether there's a proxy needed to access this particular service. And that matched completely with the user's complaint. The users said that the system they were using would freeze for minutes on end, and they'd have to sit and wait for it to suddenly spring back into life. And that was all down to this proxy resolution. So again, it's a log, it's available to us. This is netshell trace win HTTP, I think is the format. But if you look up win HTTP trace, you'll find it. Another trace that we can use to give us an insight into what's going on so that we can match it up with network packets and get a more complete picture of the cause of a problem. So just to summarise, I wanted to drop in, I wasn't sure how long this would take, so I've got a bit of time, so I'm going to drop in one other thing just to give you some additional information. But in summary, RTE model will work with 90% of your applications. They nearly all work in a request-response mode. Transum is now a part of the standard Wireshark build from 2.4 onwards. You just need to enable it. You can use RTT, round-trip time to ACK, to look at one-way delays. Logs are a great source, particularly of timestamps. That's the key. You know, as a company, Advanced 7 goes and analyses problems for customers. We're faced with literally hundreds of gigabytes, sometimes terabytes of trace data. How on earth are we going to find where the problem is in all that data? The key is to establish the time frame of the problem, and you can do that with logs. Excel has some excellent filter functions. You can filter IP addresses, URLs, anything you want. And Workbench can help you read logs with Wireshark. So the only other thing I was going to, and this is dependent on me getting Wi-Fi, which I wasn't getting earlier. Still not looking good. It's the lowercase, that one. Yeah, that's the one I tried to connect to. I don't know. It's probably... I have been having problems with my PC, I must say. I was so worried that I actually bought a spare PC with me, just in case I had problems. Okay, I don't look like I'm going to have much luck here, but the thing I was going to show you was the Wireshark community website has a load of stuff about Transum. There's a Transum users guide, for example, on the TribeLab website. There's also an SMB2 quick guide. Yeah.
You have to enable the Transum protocols?
Yeah. Analyze, enable protocols, tick on the Transum box.
And SMB, so 445.
Yep. No, you don't have to do... so, okay, that's a good question. We've got time. Let's do it. So let's have a look at how you do the whole Transum thing. So the first thing, to enable Transum, you need to be up here where it says Analyze. So we click on the Analyze, we click on Enable Protocols, and in this little box here, I type in Transum. And that brings up this. And you'll find that if you look at that, this will be unchecked by default. So you just need to check that. So that's the first thing. The second thing is Which protocols does Transum actually work on? How, does it match up request responses for all protocols? So let's look at that. We're going to Preferences, Protocols, and then choose Transum. Just here. And what you can see is, by default, there's a list of protocols. 25, 80, 443, etc. Now, you can edit this. You can add any service port number you want. 8080, 5001, which is iPerf, so I learnt yesterday. It'll also try and do it for UDP. But aside from all of that, aside from the ones that are in here and in here, it will always do DNS, it will always do SYNs and SYNACs, and it will always do SMB as standard. And in fact, I think it also does DCE RPC. So that explains that. You can set the position where your capture was taken so that it gets a better perspective on a certain number of things. This entry here, subdirector reassembly enabled, it has to match what you've got in your TCP settings. So let's look at that. Don't give out on me now. So in TCP protocol preferences, you see that we have allow subdissector to reassemble TCP streams. If you've got that set in there, then you have to have the same matching setting in the Transum entry. Let's find some Transum stuff so I can show you. So if I go in here, protocol preferences, same deal. Subdirector reassembly enabled. They just have to match, that's all. I can't go into this in too much detail, but in fact, Wireshark and consequently Transum gets a bit muddled if it sees a 1-byte packet at the very start of a trace. It doesn't quite know what to make of it. It doesn't know whether it's data. It doesn't know whether it's a keep alive. And so you can, we call those orphaned keep alive, so you can tick this box which discards them. And then you can say where you want your RTE data to be placed. Do you want it in the last request segment of the request, or do you want it in the first request? Do you want it in the last response, first response, etc.? And then you can disable Transum altogether. Yeah. Yeah. That's to do with the way that it's got more to do with the way that Transum handles retransmissions. So, if you're at the client end, you send a packet, it doesn't get any form of acknowledgement, and so you retransmit it. Transum considers that as being part of the request spread. Okay? If you set it to the server side, that you're adjacent to the service that you're trying to measure, it sees the first request, it sees a second request, and it assumes the second request is an unnecessary retransmission, that something else has happened to delay the response going back, and so it discards the second one and it doesn't measure it as request spread. And then there's an intermediate setting which basically considers everything in all directions as being part of the spread. Okay, so read about it in the Transum manual is the place to go. Look at the Transum manual on the TribeLab community website. You don't have to register to get into the Transum manual, I'm fairly sure. You can just go and look at it. This presentation? So two things. One is being recorded by Angelo there. We should have a recording of it. Secondly, I'll make the slides available. And subject to me checking, what I can do actually is, so in Workbench you can export a workspace. and what it does is it packages it all up and zips it, and then you can just import it into Workbench. I'll check what I've got. What I may do is I may export the whole package, put it on the website, and then you can just download the whole package, which means you get all the traces, all the notes, all of the links, everything. Yeah. That's one of the things about Workbench is meant for collaboration between teams, so that's one of the things that we can do. Any other questions? Well, have a great remainder of SharkFest. Hope you enjoy the rest of your day, and thanks very much for coming. Thank you.